In this example, we are going to try and graph this, and it's going to be a little bit more complicated than normal because I noticed that it's going to be irrational. We're going to have some domain issues. We're going to have to do a derivative that is going to involve the quotient rule. So there's going to be a lot going on in this one. So it's going to be a little bit of a long problem. So let's start by kind of just taking a look at, we know we have a rational. We have some domain problems. And so plus and minus 1 are going to be our domain problems. So x cannot equal -1 and +1. I also want to realize or take a kind of analyze, should that be a whole or should that be an asymptote? I know it's going to not be a whole because in order for us to have a whole, we would need a factor on the top to cancel the factor on the bottom. But this doesn't factor and this one does. So nothing's going to cancel. So both of those two are going to be vertical asymptotes. So next thing is, what about our end behavior? So we're going to have a slant asymptote because the power on the top is bigger by 1 than the power on the bottom. And if I plug in a positive number and cube it and a positive number and square it, we're going to have a positive. So it's going to be going up to the right. And then if I plug a negative, I'll have a negative over a positive, making a negative. All right, so there's our end behavior. Y-intercept is something that we can find just by plugging in 0. So 0 in a 0 is going to be a 0 over -1. So if we plug in 0, we get out 0. So it's also an x-intercept. And then x-intercepts, the others, would be taking this equation and setting it equal to 0. So we're going to take 10x to the third over x squared minus 1 and set it equal to 0. One way to do this is put this over 1 and cross multiply. Another way is multiply over the denominator to clear it out. But regardless of what you do, the denominator is going to go away because if you cross multiply it, it's going to multiply with the 0. So really the short version of this is we're going to take the numerator and set it equal to 0. And so if we take that and set it equal to 0, we would divide by 10 and cube root, and we're going to get a 0. One thing to keep in the back of your mind is you have a multiplicity on this. So a multiplicity of 3 means this is an x-intercept, but it's going to wiggle as it passes through, right? It's not going to bounce. It's not going to just pass through. It's going to wiggle a little bit. So it's going to level off for a second, right? So, and the reason is because we have a multiplicity of 3. All right. So far, here's what I have. I'm going to put this down at the bottom. So graphing wise, we have some sort of a graph that we know at +1 and -1, we have asymptotes. And we know that we have an x-intercept and a y-intercept at 0. And that's what we know. All right, so we're going to use the second derivative, the first derivative, to kind of get some more information on this. So we know we're going to have an end behavior up in this direction and down in this direction. We could find the slant asymptote by finding the, by actually dividing this in, but we'll kind of build it, you'll see, kind of based off of the first derivative and second derivative steps. So let's go into the next phase of this. So next phase is we're going to do the first derivative. So our first derivative of this is going to be a quotient rule. So we're going to do the derivative of the top. So that's 30x squared times the bottom, x squared minus 1, minus the top cubed times the derivative of the bottom, which is 2x. Right, and that's all going to be divided by the denominator squared. So if we keep on simplifying this here a little bit, we're going to distribute this and get 30x to the fourth minus 30x squared minus 20 x to the fourth all over x squared minus 1 squared. So if we put the tops together, that's going to make a 10x to the fourth minus 30x squared over our x squared minus 1 squared. All right, so there's our first derivative. We are going to do two things here. We're going to be we need to figure out where we have a zero slope, aka some potential max or mins. And that's going to be by us setting it equal to 0. But same thing here, all that ends up happening is when you set it equal to 0 and then you multiply that over, the denominator goes away. And so really that just means that the numerator is going to get set to 0 on that. So 10x to the fourth minus 30x squared equals 0. We'll factor out a 10x squared, which will leave us with x squared minus 3 equaling 0. We set that equal to 0, we'll get a 0. And if we add 3 in square root, we'll get plus or minus square root of 3, which if you plug in that, it's going to be plus or minus 1.7. All right, so we're going to get some max and mins or critical values of some kind at 0 and 1.7. So if I keep going on my graph, this is a -1, a +1, +2, -2. So we have a 1.7 somewhere around here. We're going to get some critical values to it. So let me go ahead and plug in and find some y values to this. So if I plug in positive root 3, I get 25.98. And if I plug that into the original, I would get negative 25.98. So 25.98 and negative 25.98. So we get critical numbers, call those 1.7s. All right, max mins, we don't know. We'll kind of reanalyze this once we find the critical values in our second derivative. Oh, but we're not quite finished. So we got the zero slope critical values, but we also need the undefined slope critical values. All right, not every equation has that, but since we have a denominator that could possibly be 0, that's where that's going to come from. So we'll take the denominator and set it equal to 0. And that's when we have undefined slopes, which could be a vertical slope. But we'll set that equal to 0. We'll square root both sides, which would cancel out the square and not do anything to the 0. And then we'll add 1, square root it, and get critical values of plus or minus 1. So those are undefined slopes, but they're also domain issues. So they would be values that we can't even plug in, but they are critical numbers. So when we list out and do a table and put all these pieces together, we're going to include those. All right, so on to the second derivative. Drop that down. So second derivative is us now taking the derivative of the first derivative. All right, so we're going to do the derivative of the top, which is 40x to the third minus 60x. So that's the derivative of the top times the bottom minus the top times the derivative of the bottom, and the derivative of the bottom is a chain rule. So that 2 is going to come in front times the x squared minus 1. The power is going to go from a 2 to a 1, and then times the derivative of the inside, which is 2x. All right, so there's the top, all divided by x squared minus 1 squared. Okay, so let's start to clean this up. We got a lot of cleanup to do. So we're not going to do anything with this. I am going to take this 2x times it by the 2 and then go ahead and distribute it in to there. right? So it's going to be like a 4x multiplied into those. And I'm going to hold off on that for a second because it's a little bit bigger distribution. And there's something else that I can do on this. So I'm not going to do anything with this yet. So this is just going to be 40x to the third minus 60x times x squared minus 1 squared. And then minus, that's going to be a 4x times 10x to the fourth. So 40x to the fifth minus 4x times 30, so 20x to the third times the x squared minus 1. All right, we're getting there. What I forgot to do was the denominator squared. So then that gets squared, which means our x squared minus 1 is now 4 of them in the denominator. All right, so before I do one last kind of distribution, I'm actually have this x minus 1s in common with both of them. So rather than multiplying that out twice and then distributing it into this, I can actually factor out an x squared minus 1. And then we'll remove one of them from here, remove this one totally, and then eventually I'm going to be able to cancel with one of the x squared minus 1s in the denominator. So that's a good thing. If I can remove things, that's a good thing. So I'm going to take one of these away. So that still leaves us with the 40x, put a bracket here. 40x to the third minus 60x times only one of these, x squared minus 1s now, minus, that's going to be gone entirely. So just 40x to the fifth minus 120 x to the third over x squared minus 1, but 4 of them. All right, getting there. So I can cancel one of those x squared minus 1s with one of those, leaving us with 3. So, and I'm going to go ahead and distribute the tops, and then we can combine, and then we can do the exact same stuff. We'll set it equal to 0. And so we're going to distribute the 40x to the third to the x squared. So 40x to the fifth minus 40x to the third, and then minus 60x to the third plus 60x. And then over here, we're just distributing a negative, so minus 40x to the fifth plus 120x to the third, all divided by that same x squared minus 1, but now 3 of them. All right, almost. So if I clean this up, this should be the last step of cleanup. I have 40x to the fifths canceling each other. We have a negative 100x to the third and a positive 120x to the third. So that is 20x to the third plus 60x all over x squared minus 1 cubed. All right. So we're going to do the same thing we did here. We had our derivative here, and we are setting the numerator equal to 0. So let me put that over here. We're going to take our numerator, set it equal to 0, and our denominator set equal to 0 for our critical numbers. Plus 60x equals 0, and x squared minus 1 cubed equal to 0. So we're setting the numerator equal to 0 and the denominator equal to 0. The numerator set equal to 0 is going to find us some inflection points if there's a shift in concavity. And then these are just critical points to kind of separate things out. So if we start to solve this, we have a 20x we can factor out, which would leave us with x squared plus 3 equals 0. X is going to equal 0. And then here we would subtract 3 and square root. So that would be a plus or minus an I. We are not doing those, right? We're only graphing imaginaries. So the only critical value we get as far as a potential inflection point is 0. And then here, if we cube root both, that would give us x squared minus 1 equaling 0. We'd add 1 and square root. So x squared is going to equal 1. X equals plus or minus 1. But back to, those are domain issues. So that's where our asymptotes are happening, but they're still critical numbers. All right, so let's put it all together. We have first derivative stuff. We have critical numbers at negative square root of 3, 0, and positive square root of 3. And then our second derivative, we have critical numbers at 0, and then plus or minus 1, and 1 is smaller than the square root of 3, so I'm going to put it inside. Negative 1, positive 1. All right, so now we're going to test all of our positives and negative slopes. Okay, so we're going to plug in a value. We know that this is about 1.7, so let's do like a negative 2. We're plugging it into that, but the easier version of that would be 10x squared, and then x squared minus 3 over this thing squared. So we're plugging in a negative 4. Good news is the denominator is going to be positive. The numerator is going to be positive here. So the only thing that I'm really caring about is what happens when I plug a negative 4 in here. And that's going to be negative. And then again, these are positives no matter what. So I'm really just focusing on here. If I plug in a value like a negative 1, square it, negative 3, that's also a negative. Some of my critical numbers. I have 5 critical numbers with my first derivative. So let me sneak that in there. At 1, negative 1, and 1. All right, let's try again. So if I plug in a value between 1.7, negative 1.7 and negative 1, like a negative 1.5, I got a positive, positive, and a negative 1.5 squared is a 2.25 minus 3 is still negative. Don't forget that these are asymptotes. Right, that's kind of what's happening at those spots. And then from negative 1 to 1, like a negative 0.5. So that would be half, a quarter, minus 3 because we're squaring it. So that would be also a negative. Right? And then 0, like a 0.5. That's going to be the same thing as the negative 0.5. So that's a negative. And then I need to analyze that one more time. 1 to here, we're going to do like a 1.5. So 1.5 is 2.25. So that's still a negative. And then actually out here, I needed something more like a negative 2. So a negative 2 squared will give us a positive. And again, those are positive, so I don't matter about those. And then if I plug in a 4 over here, that'd be a positive. Holy cow. All right, so we have negative 3 and 3 were our critical numbers that weren't domain issues, like these two, right? And 0 was our other. So those are the 3 that I'm really focusing on because I know these are asymptotes. So we have a positive slope transitioning to a negative. We have a negative slope transitioning to a negative, and we have a negative slope transitioning to a positive. Good. We only have 3 critical numbers for our second derivative. We are plugging it into here, which again, there's that look for the numerator. So 20x and then x squared plus 3 over x squared minus 1 cubed. So if I plug in a value here, like a negative 2, we have a negative. And then a negative squared plus 3 is positive. And a negative 2 squared minus 1 is going to be a positive cubed is positive. So that's going to be a negative, meaning concave down, which agrees. And then here, between negative 1 and 1, so a negative half. Oh, let's see, negative half is negative. Negative 1/2 squared plus 3 is going to be positive. Negative 1/2 squared is going to be a negative. Cubed is going to be a negative. So that's going to be positive. So concave up. And then positive 1/2 will be a positive, positive, negative. Concave down. And then finally, last thing, we got a value that's greater than 1. So like a 2. So that'd be a positive, positive, positive. All right, so all of that is what we were looking for. So we have this maximum, and so that means this graph did that at that point. We have a maximum and it's concave down, so that totally agrees. And then we have a concave up to 0. So it's going to look something like that, and it should level off because of the multiplicity. Right, so that's concave up, but it doesn't keep on going to finish the concave up because it transitions into a negative slope and it goes concave down at that spot. And last bit is we have a minimum. So we're hugging the asymptote and then doing something like that. And so we have this concave up look to it. We have negative slopes transitioning to positive slopes. So that was about as ugly as it gets. Thanks for hanging in there. And then it just kind of becomes a mess because of the kind of derivatives that we got going on. But that was everything we could possibly do with our first derivative, second derivatives, and kind of our calc and pre-calc stuff.